Hello. So in this video, we're going to be talking about Brownian motion. Okay, we're kind of be talking fairly generally about Brownian motion, but then we're going to kind of try and apply it to the situation that we need to deal with here, because it's really important. Brownian motion describes a lot of the stuff which happens. You know, how financial markets behave is often described using Brownian motion. So Brownian motion is a really kind of important thing. Okay, so first of all, what we're going to start off with is just some kind of properties. Oh yeah, by the way, Brownian motion may sometimes be called Wiener motion, I think it's called, or Wiener motion. It's exactly the same thing. All it basically is, Brownian, the guy, I think somebody called Brown, observed this kind of motion to start off with, but couldn't really explain it. And then along came Wiener, and he was, or Wiener, and he was able to explain it. So basically, Brownian observed it, or Brown, or whatever the name is. I think it was Brown probably. He observed it, and then Wiener came along, and he was able to then explain that motion. But it's often just called Brownian motion. That's absolutely fine. But it may sometimes be called Wiener motion as well. Okay, so basically, the idea is that you've got this kind of Brownian motion which goes on, and effectively it's related to a random walk. And we'll come on to kind of, you know, how we derive it and stuff. But effectively, Brownian motion looks something, you know, it's very random kind of thing. It's, you know, it's very jagged and everything like that. So basically, this is what's going on. Okay, so this is the Brownian motion. So Brownian motion, let's call it BT, against time. So basically, as we move through time, you know, we follow this kind of graph, this kind of progression, and we call that progression B. Okay, the value at that point in time. Okay, so this is effectively just what's going on. So first of all, what we're going to start off with is just some properties of Brownian motion. We tend to call it axioms. They're the types of things that, you know, you can't really prove, but they're kind of intuitive that they should be true. And from those axioms, you know, everything else is built from them. You know, an example of an axiom in kind of real, you know, the familiar, you know, perhaps with some familiar example, is just 1 + 1 = 2. Okay, when you add two numbers, you should get a third number. That's an example of an axiom, for example. Okay, well here we've got we've got 4 axioms of Brownian motion. The first one is that Brownian motion, so Brownian motion, I'm going to call it BM, okay? Brownian motion has what's known as independent increments. So what that obviously means, okay, because as we move through time, we obviously move through Brownian motion as well. Okay, so basically an increment is just an increase in time, effectively. So it's what we're basically saying is that as we move through time, each increment is independent of the other increment. Okay, so for example, if I just draw the time, okay, time going on here, okay, and say if we have a time value, I don't know, let's call it R, and let's have another time value, let's call it S, let's have another time value, let's call it T, okay, and at each time value we have a Brownian motion associated with it, so let's call the Brownian motion associated at at R, BR, let's call the Brownian motion at S, let's call it BS, and let's call the Brownian motion associated at time t, let's call it bt, okay? So effectively, what we're saying is that the Brownian motion, so, you know, are you happy that from S to t is an increment, okay? S to t is an increment, okay? And it's going to be, it's going to be some increment, okay, from S to t, okay? And what we're basically saying is that that increment from S to t is totally independent of other increments. So, say, for example, from R to S. Okay, so in other words, whatever happens in this time period is not dependent of what happens before it. Okay, so this time period is totally independent. It's not related to at all the time period that comes before it. Okay, so it's kind of this whole idea behind, you know, Brownian motion is completely random. You know, this kind of makes sense. That basically whatever happens in this time period here, it doesn't matter about what's come before. Okay, it doesn't depend on what's come before, so it's totally independent. Okay, so that's what independent increments mean. The second axiom is basically saying that Brownian motion has what's known as stationary. So it's stationary increments. Okay, increments. So not only is it independent, so in other words, those, you know, the increment, whatever happens in that time period there, doesn't depend on what comes before it, but it's also the increments are stationary. So in other words, it's kind of related to that, I suppose. In other words, what this is saying is that the distribution, okay, so whatever happens between BT and BS, so the increment there, the distribution of that depends entirely on that time value, okay, no other time values. It only depends on the time values going from here to here. Okay, so whatever happens, whatever the Brownian motion is doing, say for example, this is t and this is s, whatever the Brownian motion is doing between those two time values, okay, depends only on the time values and nothing else. Okay, so it depends only on the time. So it's what's known as stationary increments. Okay, the third axiom is that the distribution is normal. The distribution is normal. So in other words, let's look at the distribution which happens between BT and BS. Okay, so BT and BS. So this distribution in here, whatever happens to this Brownian motion, let's just draw a Brownian motion in. There we go. So whatever happens in that time period, in that Brownian motion of that time period, is what's known as normally distributed. And this is what we're going to look at in a little bit more detail later on in the course. So this is normal distribution, so that's why we use a capital N, okay, of mean and variance. So this is mean in this one, and then we've got variance over here, okay. And what are those mean and variances? What are those mean and variances? Well, it's going to be mean, okay. Mean is sometimes called drift, by the way. Sometimes we call it drift. And then we've got variance as well. So drift is just basically where you normally denote mean by mu, okay. And variance is going to be, well, it's the square root, it's the square of standard deviation, right? Variance. So we normally denote it mu and sigma squared. You should be fairly familiar with that from statistics, right? But it's going to be from S to t on that increment. So in other words, we're going to have to multiply it by that increment. Okay, so we're going to have to multiply that by that increment. Okay, from S to t. So this is the normal distribution of that increment there from BT to BS. The Brownian motion at that increment is normally distributed, so it follows a normal kind of pattern, normal distribution. All the data between, all the data of the points in between that time increment is going to be normally distributed with mean and variance, and the mean is some value which we call mu. Okay, that's normally the mean. Okay, multiplied by that time increment there from t minus s, and the same kind of thing with the variance sigma squared multiplied by t minus s. Okay, then the fourth and final axiom is that basically BT, so the Brownian motion, okay, has continuous sample paths, has continuous sample paths. Okay, so all that basically means is that at any time value we like, we can select any time value. Okay, it will always be continuous at that time value. So there's no jumps, there's no kind of discontinuities at all. Okay, it's continuous. Remember what remember what continuous means. It basically means we can draw the graph without taking our pen off the paper. If it's discontinuous, we have to take our pen off the paper. For example, that's an example of a discontinuous graph, because you've got a jump which happens in the middle there. Okay, so that's all the four axioms are. Okay, I'll write them out in neat now. Okay, so here they are, all written out in neat. Commit these to memory, okay. These are kind of the things, well, don't commit them to memory, you just kind of bear them in mind when you're dealing with Brownian motion. Notice as well that, this is kind of the general case, so a time increment, right, because we're looking very much at increments now. But notice if it was just the Brownian motion at some time, then it would just be normally distributed under the suspected, under mu t, and then sigma squared times t. So in other words, the time period, your particular time. So it's just a normal distribution, effectively. Okay. So, okay, now let's look at a very, very special case of Brownian motion, which is what's known as standard Brownian motion. Okay, so I've already kind of built up the idea that, Brownian motion is related to normal distribution. Okay, remember that normal distribution pretty much describes every single, everything which happens in the world. Okay, two things can be connected normally by what's known as a normal distribution. Normal distribution is a really, applicable way of describing a pattern between data points. Okay, so basically, standard Brownian motion. You can have a standard normal distribution, which is the case when the mean is 0 and the standard and the variance is 1. Okay, so let me just write this out. Okay, you can have a normal distribution normal distribution with mu and sigma squared, right? And the standard normal distribution, okay, so this is x is normally distributed with that. Well, you can convert it into a standard normal distribution, so we normally call it z, is normally distributed with a mean of 0 and a variance or standard deviation of 1, right? Because it's still going to be 1 squared. And effectively, if you draw out the normal distribution, that just basically means that you put the centre point at 0, okay, and each time step above the mean, or each step above the mean, is just going to be 1. So this is -1, -2, -3. This is 1, 2, 3. And normally all values are pretty much done within 3 steps of the mean. I think it's something like 97% or something. I don't know. Or it might be, I can't remember what it was. I think 97% is actually when you get to 1. 90%, 7% of the values. But basically all of the values that your random variable can cover are pretty much done within 3 steps above and below the mean, effectively. Okay, so just a quick reminder of normal distributions there. So obviously standard, if that's normal distribution where so a standard normal distribution is where mean is 1, okay, and the variance is, sorry, the mean is 0 and the variance is 1, then standard Brownian motion is exactly the same, okay, because standard Brownian motion obviously follows, you know, bt minus bs, that follows a normal distribution, so a time increment from t to s, the Brownian motion time increment, okay, remember this thing here, Brownian motion time increment follows a normal distribution of this, t minus s, sigma squared, t minus s, okay, it follows a normal distribution. Well, if mean is 0, so if the standard Brownian motion is just when the mean is 0 and the variance is 1, okay, then obviously bt minus bs, okay, becomes a normal distribution of 0 times this thing, and then just 1 in here, so just t minus s in here. Okay, so, you know, we've got t minus s going on in here, so that's another thing. And also, we have to say that Brownian motion at time 0, so in other words, when we start looking at something, we call that kind of initial Brownian motion. As soon as we start looking at, say, like, if we're looking at financial markets, the point which we start looking at, we call that the initial point, okay, so when time equals 0. Okay, so we basically assume that at the very start, we start at 0. It was standard Brownian motion. The time at the start is always going to be 0. Okay, because if you like, this is where we start from. Okay. So these kind of axioms, these kind of things need to be you need to bear these things in mind when you're dealing with Brownian motion.